Really helps for number one if you redraw the two triangles. So I'm going to redraw the small triangle over here, BCA, and the large triangle over here, DEA. AC is from the small triangle. BC is also from the small triangle. So DE and AE should be from the big triangle, but they should correspond to what's next to them. Does AC correspond to DE? No, it does not. AC corresponds to AE. So number one is out. Number two, AB is from the small triangle, AD is from the big triangle, and those two do correspond. BC is from the small triangle, DE is from the big triangle, and those two do correspond as well. So number two is the correct answer. Number three is incorrect because CE is not part of either of the two triangles. CE is just a part of this trapezoid-ish thing over here. And for the same reason, number four, oh wait, no, it's not the same reason. So for number four, DE is from the big triangle right over here, big. BC is from the small triangle, and those do correspond. So this should be big over small. Let's check it out. So, oh, DB, yeah, this is the same reason. DB is not a side of the triangles. It's part of that quadrilateral at the bottom. So 2 is the correct answer. For number 2, we have that MN is 8, we have that ML is 5, and we have that NL is 6. And now we need to find the perimeter of trapezoid BMNC. So we have midsegments here because we have midpoints connecting the sides together. So if MN is 8, since it's the midsegment of to the side, this side's 16, so this is 8 and 8. And if this is 6, this side's 12, so 6 and 6. And if this is 5, then this is 10. So we have 5 and 5. We need the perimeter of this quadrilateral. So that's going to be 6 plus 8 plus 5 plus 16. And that is 35. For the next one, triangle TAP is dilated by a scale factor of 0.5. So TAP is the larger one. And when it's dilated, T prime, A prime, P prime is the smaller one. So number one is not going to be true because before and after a dilation, angles stay the same. Similar triangles, angles are congruent. So that's not true. Same thing for number two, the angles do not change after a dilation. Angles are congruent before and after a dilation. Number three, TA is double T prime, A prime. That is absolutely true because TA is before the scale factor dilation of 1/2. So the dilated one is smaller. So the original one is bigger. Number four, we need to find the length of DE. It really helps again if you redraw your small and your big triangles. So I have CDE and I have CAB. CD is 15. CA is 15 plus 9, which is 24. And then DE is what we're finding, and AB is 40. So now when I make my proportion, I can easily see that 15 and 24 correspond, and that X and 40 correspond with each other. And from here, all I have to do is cross multiply and solve. Let me double check that on my calculator 1 second. 40 times 15 is 600. So we have 600 is equal to 24x. When you divide both sides by 24, we get that 25 is the correct answer here. Okay. For number 5, we need the scale factor of dilation that maps ABC onto RST. So the reason why it's 1/3 and not 3 is because we're getting smaller. This is the pre-image, this is the image. 1, 2, 3, 1. It's getting 1/3 of the size. So the answer is 1. For the next question, number 6, For which one are the triangles not similar is what it's asking. It's asking when this statement that the triangles are similar is not true. So it's asking which ones are not similar. So in the first one, the inner triangle and the outer triangle have corresponding angles congruent. And they also have the shared angle. So that is true. I do see AA. For the second one over here, between these two triangles, they do have two pairs of congruent angles. They are the alternate interior angles, and they are congruent through the marking. So that's AA. Here we have the congruent right angles, and we have the congruent vertical angles. So that leaves this one. These are the two triangles that we're interested in. And between these two triangles, there's only one pair of angles. The other pair of angles is not within those triangles. So this is only 1A. So this is the one that we're looking for. Number 7, we asked you guys not to do, but if you were going to do this one, you are proving the big triangle BCA similar to the smaller triangle on the left. So they share angle A, and angle ABC is a right triangle, and CD is perpendicular to AB, so this is a right angle as well. So all right angles are congruent. Shared angle, that's AA. Okay. For this one over here, we have AF parallel to CT, and we have AF congruent to CT. So what this means is that this is a parallelogram. So since it's a parallelogram, and once again, it's a parallelogram because if one pair of opposite sides is both congruent and parallel, then that means we have a parallelogram. So since it's a parallelogram, I know that the other pair of opposite sides is also parallel, which means that these alternate interior angles are congruent. And I know I need those alternate interior angles because if I look at the proof statement, we have AB, we have TE, we have AE, and we have TR. So these are our two triangles that we're focusing on. In addition to the alternate interior angles, the only other thing we need is the vertical angles. And then we have triangles are similar due to AA. After you prove the triangle similar due to AA, you need to prove a proportion followed by a product. When you make your proportion, just take the segments from the proof statement and put them in your proportion. The only thing you have to be careful to do is double check that when you cross multiply, it gives you the product that you need. So here, notice how mine, oops, I just messed this one up. Notice how mine does. And the same reason every time when you're proving a proportion, corresponding sides of similar triangles are proportional. And then last step comes your proof statement. Because in a proportion, the product of the means equals the product of the extremes. Once again, just a fancy way of saying cross multiplication. Here is the full written up proof. Notice how it has that the quadrilateral is a parallelogram and how I know that. And then it has the alternate interior angles. Before the alternate interior angles, you do have to say that this pair of sides is parallel due to the fact that we have a parallelogram. Opposite sides of a parallelogram are parallel. The alternate interior angles, the vertical angles, so the triangles are similar. Then the proportion followed by the product. Okay, for this one over here, we have a line dilation centered at the origin. So the first thing I'm going to do is I'm going to take the equation of the line provided and I'm going to solve for y. So I'm going to subtract 3x from both sides. And I have negative y equals negative 3x plus 4. Then I'm going to divide by negative 1 to get y by itself. So I have y equals 3x minus 4. So when you do any dilation, the slope stays the same because it makes a parallel line and parallel lines have same slopes. When you're centered at the origin, you can just take the y-intercept and you could multiply by the scale factor. So the equation of the dilated line would be y equals 3x minus 8. For this one over here, we have a rhombus. In a rhombus, just like a parallelogram, the diagonals bisect each other. But unlike a parallelogram, in a rhombus, the diagonals are perpendicular, so they intersect to form 90-degree angles. So if AC is 18, each half is 9. If BD is 24, each half is 12. We have right triangles here. So we can find a side of the rhombus by using the Pythagorean theorem. I'm going to take a second and just add those two on my calculator. 81 plus 144 is 225. So we have 15. If you take the square root of both sides, you get 15. And we need the perimeter of the rhombus, so we need to just multiply it by 4, because there's 4 equal sides on a rhombus, and we get 60. Okay. Over here, the best way to approach these kinds of questions when you have a big right triangle with an altitude dividing the triangle into two smaller triangles is to redraw the triangles. So I'm going to redraw the big triangle and the other two triangles so that they're all facing the same way. You want to make sure that you do put the right angle in the same spot on all of them. So C is the right angle in the big right triangle. Now it doesn't matter if I put A here or B here for the original big triangle. What matters is that I'm going to be basing all of my other ones off of this first one. In these smaller triangles, I'll do the medium one next, ACD. The right angle is at D. And this triangle is inside the big triangle, and it shares angle A with the big triangle. So since angle A is on top on this triangle, I need to put it on top here because it shares it with the big triangle. And that leaves C to be over here. And then for the last triangle, the small one, the right angle is once again at D. And the small triangle shares angle B with the big triangle. So if angle B is here, I need to put angle B in the same spot, and that leaves C to be up here. So now I have the triangles labeled correctly. So let me label the numbers. So CD is H, that's what we're finding. So I'm gonna just label, CD is H, and there's two CDs. It's on two of the triangles. AD is 12, so here's AD, 12, and BD is 3. Okay, so now I can easily see the sides of my similar triangles. So 12 corresponds to H corresponds to 3. Let me cross multiply. That's 36 is equal to H squared. So H is equal to 6 when you square root both sides. So that's all we're finding here. We're only finding the value of H, so the value of H is 6. For the bonus, I definitely do want to go over it in this video. So what I'm going to do in this bonus is I'm going to use my compass and I'm going to dilate it by 1/2. Since we're dilating by 1/2, we are actually making the triangle smaller. So what that means is we should be moving it closer to the center of dilation, and it should be half the size of the original triangle that we are provided with. The center of dilation here is C, so C is not going to change. C is going to stay in the same spot. So what I'm going to do for the other points, not C, because C is not going to change spots, is I know that point A, point C, so the pre-image, the center of dilation, and the image point need to all be located along the same line. So they're all going to be located on this line. I know it's going to be in between A and C, well, actually halfway in between, because it's going to move closer to the center of dilation, not further away because we're getting smaller. So in order to get the halfway point, the midpoint, I'm going to do a perpendicular bisector. And I'm not going to do the full circle. I'm just not. Just being really careful not to change the angle on here. It's so difficult on the computer. So much easier. Okay, and you should have a top intersection and the bottom intersection. So we're going to just connect through both of those intersection points. And that is the midpoint. And since that is the midpoint, that's halfway closer to point C than A was. So that's point A prime. Okay, I'm going to do the last one now. Only have to do one other point. I'm going to do point B. So the image will be located along that line. It'll be located halfway between B and C. Okay, this one's shorter. Can use a shorter length. Once again, I'm not going to make the full circles. I'm just going to do so that way you could see the arc. I'm going to be very careful not to change the distance. Oops. Okay. And it could get a bit messy, especially on this computer. So annoying. Okay. And there we have point B prime. So I'm just going to outline the dilated triangle. I did a really bad job of connecting that last line together. Here we have the dilated triangle, half the size of the original, and it shares point C with the original.